Okay. So for outline today, okay, maybe we will see the representation of the molecule structure, okay, in terms of vector building blocks, okay, and what is how can we present, okay, in terms of atoms, and also generation of the molecules and mixture candidates. This is the important part of this chapter actually. Okay, is it stable or not your compounds? Okay, is it can in terms of binary mixture, is it you can mix together or not your compounds or your molecules? Okay, so that one is for the mixture blends. Okay. Um. So if you look at here, what's next for the problem formulation algorithms? Okay, if you look at here that the objective of the problem formulation algorithm is actually to transform the qualitative problem specification, okay, into quantitative one through a combination knowledge, base, insight, and also experience. Okay, so this is the multi-step process, and we are required a different level of information. Okay. So, in summary, the step that we need conducted it consists of six steps. Okay. First, we have to retrieve this one. Okay, the number one, we have to retrieve the known properties of the component. Okay, compounds that to be used in the design compound. Okay, this one. And then second, we have to obtain the system temperature, pressure, compositions, okay, along a pressure along with the compositions, okay, for the compound in the system, okay. And third, we have to extract the list, okay, of relevant pure components, okay, and mixture properties from knowledge base. Okay, this is a step number 3. And then we have to identify property models, okay, available for the estimation of the properties, okay. List the molecule type that can be handled by the property models, and the last is from the list of the compound types, okay, for which property prediction method exists. We create the list of the building blocks used to assemble molecules in design phase. Okay, so this is a 6 step. We can summarize. Okay. So for the database actually is containing information on the type of the molecules, okay, versus the building blocks. Building blocks is, for examples, groups, okay, as well as uh, type of molecule versus EH and S properties, okay, which can help in the problem formulation. Okay, for example, this is a functional groups, right? You look at here that such as OH and COH group in the set of the building blocks. So this functional group actually is must exist in alcohols and also acid. Okay, for OH is alcohols, and COH or COH is for the acid. Okay, so selection of the molecular types such as alcohol and acid, okay, can be linked automatic as a selection in the building blocks, okay, for these functional groups. Okay, so we cannot omit, or if you want to design the acid, COH must be there. Okay, so on the right side is the example of the simple monofunctional molecules. This one. Okay, we have acyclic hydrocarbons. Okay, aromatic hydrocarbons, alcohol, ketone, ester, and acid. So I think this one you already learned in the organic chemistry, right? So the building block, if acyclic, CH3, CH2, CHC, right? If aromatics is the aromatic compound lah. This one 6 ring in rings. Okay, so you have to remember ketones. So this is the ketones lah. Okay, ketones including ether lah. Okay, there's a H here, and this one is a R and R, R1 and 2. Okay, ester, this one is ester lah. Okay, and acid, COH lah, this one. Okay, So this is the building blocks. Similarly, also for the aromatic compound, maybe it's a carcinogenics and chlorides. Okay, maybe corrosion and have negative impact on the environment. Okay, so if you choose E, H, and S properties as a constraint, meaning that boundary, so automatically we have to exclude for these compounds. Okay, in the building blocks if you consider E, H, and S properties. Okay, so what's next is actually is we want to design is a design phase of the CMD methods. Okay, so let's see the molecular structure representation. Okay, how can we represent the molecular structure? Okay, so if you look at here is if given the quantitative problem specifications, okay, the objective is to apply a suitable method, okay, for generating the feasible candidate. Okay, here the feasible candidates can be a set of molecules or mixture that satisfies all properties constraint and reflect optimum condition. This is including the molecules or mixture. Okay, so it can fit with the can reflect with the optimal performance, not only the molecules but also the mixture. Okay, uh, okay. So in order to generate the feasible candidate, so we have to know how to represent the structure of the molecules. So how can we represent of the molecule? Actually, we have 4 or 5, A, B, C, D, and E, I think. Okay, so we can represent. Okay, I think until F. Okay, whether until the fragment based metric and also atomic based metric. 5, 6. I think it's 6. Let's see the the representation of the molecule structure. Okay, the first one is the simplest form. Okay, this is the simplest form of the molecular representation. It's based on its chemical formula. Okay, C5H10O2. If you Google that in Wikipedia, you can get this is the simplest form. Okay, so represented by the type of atoms, it contain a number of the occurrence of each atom type. Okay, so is actually is represent a large number of compound of very different types, but we cannot actually there's a constraints here. Okay, no information regarding on the bonds in the compounds. This one we actually is very general, right? We don't know the bonds here. Okay, it's quite difficult. Okay, and another this one, but no information on the bonds in the compound. So this is the constraint. Okay, and then representation. Another one in terms of the molecular representation is the collection of the functional groups or fragments. Okay, so a functional group is a molecular fragment or the substructure. This one. So we know the bond. This is double bond, single bond, right? Uh, this is we can define as a number and type of atoms. Okay, showing how atoms are connected and how many free bonds connection and the atom on which the free connection are located. This is about the location. Okay, so this is a second type. The third type is and fourth, number 4 is a CND. If you look at here is a group factor. Another one is a group factor. Okay, is contains some of this connectivity information, but does not define completely. Okay, a group vector can be represent also isomer. Okay, we can see here in D lah, can be represent as isomer. Okay, actually is a different compound, right? This compound. Okay, and also if you know the balance of the different types of molecules, so we can generate the bond configuration. Okay, so this is a type. Now C is a group factor and D is more to represent isomer. We can form from the group vector. Okay, isomer like a cheese, trans, EZ, that is a isomer. Okay, okay. So uh, another one is in term of adjacent matrix. Okay, from the group vector and also especially from the group vectors and also the building blocks and atoms, we can present in term of the matrix. Okay, so one of the simple and flexible way to define the connectivity actually is by using the adjacency matrix. If you know, a matrix is like a blocks, right? Okay, like a blocks. This one. If in mathematics, it's like this lah. So it's adjacent matrix. Okay. Simple and flexible way to define the connectivity by using adjacency matrix. Okay. Square symmetrical matrix with row and column representing each atoms or fragment in the molecules and containings. Actually, we can present in terms of fragment as well as atom. Fragment is a fragment like a CH3 lah. Okay, CH3, CH2. This one is fragment. If atoms, adjacent base matrix is like a H, C, O, and so on. It's more to atom. Okay. Non-zeros indicating the number of bonds. Zeros indicating the number absent of bonds. Okay. So you have to remember that. Okay. So if we present in terms of the fragment base matrix, okay. If you look at here, that conversion from fragment base matrix to an atom base matrix is achieved by replacing the entry for each fragment with the atom adjacency matrix representing the fragment. Meaning that if you look at here, okay, so this is the fragment for CH3, CH3, CH2, CH2, COO from the previous molecules. Okay, so if you look at here, CH3, CH31 lah, and we have two CH3 right here. Okay, CH31, the adjacent for CH2 COO is equal to 1 lah. Okay, that's why we put it as 1. Okay, and CH2, CH3, CH3 equal to 0 because it's adjacent, right? Just next to the CH3. Okay, okay, that one is for CH3 lah, CH31 lah. For R1, this one R2. Okay. Okay, how about the second CH3, right? For second CH3, if you look at here, the adjacent fragment is only CH2, meaning that this one only one. How about CH2? Okay, for CH2, if you look at here, that here, right? For CH2, we have one for CH3, and we have this one, and also we have one for CH2COO. Okay, this one the one. Okay, and CH2COO. Okay, if you look at here, that CH3 1, CH2 2. So because this one, right? So adjacent is CH3 and CH2. Okay, so for both isomer lah. Okay, when we present in the fragment this matrix. Okay, easy, right? Okay, for the atom base matrix, okay, when we express in the atom for the compound D lah, this one same, this one, right? Isomer. So if you look at here, that no stirring information to distinguish isomer. Okay, so if you look at here, you just what is it, detach all the the atoms from the molecules, okay, and put it as a matrix. Okay, adjacency matrix. So if you look at here, how many H here? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So meaning that 3, 3, 6. This one is 1. This one is 1. Oh no, this one we have 2. 10 lah. Right. 6, 10 total. So let's see the first H. Okay. The first H here. For CH3, right? So the adjacent is only because there is a 3, right? This one, this one, this one. Okay, so H lah, 3. Okay, how about another H? Similarly, 1, 1, 1. Okay, and so on. You can write in terms of in the tables or as adjacent matrix, all the atoms, okay, which is connected. If for O here, Oh, we have what is it? C. Oh, we have C here. We have another C. What else? Only that one, only C, right? And no more, right? Okay. Okay. So it's easy in terms of uh, atoms. Okay. If you want to distinguish the isomer, okay, I think you need 3D information lah about the atom placement. This one is through the 2D relation between atoms lah. Okay. So we have to consider the X, Y, and Z 3D lah, and also like internal coordinates. Okay. If you look at here, that already uh, shown in the slides. Okay. So you need the internal coordinate system using a bond, length, angle, torsion angles. Okay. And then you have depending on the computation to be performed involving 3D representations. Okay. So all this you need if you want to distinguish between the isomer. Okay. So let's see the representation of molecule structure and the estimations because they have 4 levels. Okay. So if you look at here, this one, they have 4 levels. Okay. So if you look at here that for the level 1, okay, for level 1s, this is represent as in term of group contribution methods can be employed. So this one in term of uh, just now is a fragment side in term of the fragments. Okay, and then we can step 2 level 2 is this one is more to what we call uh, this one is in term of the group vector lah. This one is fragment. Okay, this is a fragment matrix lah. This one is fragment matrix, and this one is a atoms matrix lah. And this one is 3D. Okay, so actually for the fragment, we need the additional information of group connectivity, which can be used to improve the estimation lah. This is a second order. Okay, and then this one is a more to the molecular connectivity. Okay, for the atoms. Okay, and the third one is a 3D. This is I told you is about the isomer. Okay, actually we only cover until level 2. Okay, just representation of molecule by functional groups level 2. So we will apply only until level 2. Okay. Okay, I think all of you already understands about the fragments, a base matrix, and also atom base matrix. Okay, so please take one paper. Please do this activity. Okay, activity 4. For these two chemicals, propylamines and ethyl benzoate, I think this is just a propylamine. Okay, you choose only propylamine. Provide the molecular representation using the following chemical formula, group vector. If you have a textbook, please refer to table 4.2. Okay, 4.2. Okay, that is all the basis set for the functional group. And please construct the fragment-based agency matrix and atomic agency matrix. Okay, please answer in the piece of paper. And then please submit. Please post in the Jamboard. This one atom-based matrix, and this one is fragment-based matrix. Can you do one piece of paper? Please submit. I give you the Jamboard link. I give you about 10 minutes. Jamboard. Please do first before I give you the link. Go to page 11. Go to page 11. Jamboard. Okay, this one. Activity from share. Filling. This one Jamboard. Okay. Here's this link. Part 3. Activity 4. Okay. Please go to page 11. I have no answer, so we can discuss once your friend paste in the Jamboard. Okay, I want to say first number one chemical formula. You have to write, okay? Number one chemical formula, group vector. What is the group vector for the propylamine? Propylamine. I think it's better you write in the A4 paper lah, and then you paste as a picture. This one is one by one. I don't think. This one. Please refer to for the group vector. Please refer to the table 4.2. Okay. No group vector. How about B, C, and D? 1, 2, 3, 4. Okay, what is the building block vector? I think uh the fragment is for NH2 is not available there, right? Okay, no answer. What's that? CH3, CH2. CH2, CH2, NH2. Okay, possible. Okay. And then fragment and atomic base. What's that? The structure, what the ethyl benzate? I told you it's only propylamine. Okay, if no answer, I just give this one as a tutorial lah. Okay, and later you can send via e-learnings. Since nobody answer the activity form. So meaning that the tutorial is going to be additional questions. Okay, it's okay. Since already 11:45, so we continue. On the generation of molecules as mixture candidate. Okay, so for the generation of the molecule candidate, I think this is importance. Okay, because we have to know that your molecule is feasible or not, or stable or not. So we have to check by using Odile and Monkey auto rules lah. Okay, so in this subsection, first molecule structure generated. Okay, and then we will focus on the mixture blend candidates lah. Okay, so if you look at here that this one. Okay, so generation of the molecule structure, since the aim is to having the given functionals, having the functional group as a building block and a set of rules to combine them into chemically feasible molecules. Okay, is needed to generate the candidate structure lah. Okay, so this rules is limit to the combination of group produced in chemically feasible molecules fewer than total number of unrestricted combination. Okay, for example, if you can hear that given the group of CH3, CH2, OH, okay, so you have to determine how many chemically stable molecules can be generated within minimum of two groups. Okay, so meaning that minimums two group. Okay, so you cannot generate one one fragment, okay, like or CH3, only CH3 cannot. So minimum of 2 groups, okay. Maximum of 3 groups, okay. So you cannot do CH3, CH2, 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 CH3. That is already 4 groups, okay. Only maximum 3 groups. And the condition that the OH functional group appears no more than once, okay. So meaning that your molecule cannot be diols, okay. CH2OH OH is not possible, okay. So it's only appear as a once, okay. So can you generate? I think the answer is there, okay. So if you look at here that which one is a stable, okay, which one is a stable. So if you look at here, uh, which one is the feasible? If you look at here that this one, okay, minimum is 2 group, minimum is 2 group, but this one is appear no more than once, okay, no more than once, okay. So meaning that without OH is possible, okay. CH3, CH2, CH3 stable. CH2, CH3, CH2, OH is also possible. OH, OH, this is not feasible, okay, because this one, right? Because of this statement. OH fraction will appear no more than once. How about this one also? Cannot. And this one? This one is not feasible or not stable because CH2, CH3, there is a valence here. Okay, because it's not stable. Okay. Okay. Is it clear?
Yes, doctor.
Okay. Okay. So in order to ensure the molecules are chemically feasible, okay, you should follow the Odile and Macchiato rules lah. Okay. So look at here that there is 5 equation that you have to follow based on the Odile and Macchiato. Okay. Question number 1, question number 2, question number 3, question number 4, and question number 5. So if you look at here that the definition for each symbols, okay, like the M is the number of the distinct group in basis set. Okay, Q is a represent as the whether your molecule is bicyclic, monocyclic, or acyclic. Okay, if bicyclic, you want to determine the bicyclic molecules, it should be -1, the number. Monocyclic is equal to 0 and acyclic is equal to 1. Nj and Ni is number of group J and I present in the molecules. Okay, so for example, if you have a CH3 and CH2, right? So Nj you define as a J you define as a CH3 lah, and the rest CH2 is I. Okay, or you define CH2 as a J, and the other one, the another one CH3 is as a I. Okay, and the ones okay. Uj is the valence group. Okay, the number of free bond connections. Like a CH3, the valence group is only 1. CH2 valence group is 2. OH is equal to 1. Okay, so you have to remember that one. And N max, maximum number of group allow. How many molecules you can generate? For examples, it's already stated that boundary, just like now, right? Okay, the maximum number is only 3. This one. Maximum of 3 groups. That is the N max. Okay. N equal number of group present in the specific molecules. How many? Okay, NJL and NJU is lower and upper bounds. Specified number of allowed group of type J. So generally for the lower bound is must be 0. Generally is equal to 0. Okay, for the lower bounds lah. NJL this one. Okay, we set as a 0 generally. Okay, upper bound is depending on how many how many groups possible in the molecules. Okay, for example, this one, right? the minimum of 2 groups, maximum is 3 group. Okay, maximum is 3 or 2. Okay, we can generate lah. Okay, so how can we use these equations? Okay, so let's see within 5 minutes. Okay, if you recall back the previous example on CH3, CH2, and OH, okay, given the group of CH3, CH2, and OH, how many chemically stable molecules can be generated with minimum of 2 groups and maximum of 3 groups? And the condition that the OH group appears no more than once. Okay, so if you look at here that we have CH3, CH2, and OH. Okay, UJ is what? UJ, valence group, right? UJ is valence group. So meaning that if you look at here that we is annotated. Okay, this is one, right? Because can take only one group. This one is 2, right? CH2. This one is only one valence. Okay, lower bounds we set as a 0. Okay, in either one are generated. Okay, it's okay if we don't want OH or CH2 or CH3. That's why is the lower bound is 0. Okay, it doesn't matter. Okay, upper bound. So if you look at here, that is the maximum number compound that we want. How many? Okay, is it okay if we want one OH? Okay, or 2 CH2? It's possible, right? Because maximum is 3, right? Maximum is 3. Okay, so maximum we possible for 2. CH3 also possible. Okay, because maximum is 3. So if CH3 also possible. That is more possible, right? Okay, but if CH2 and CH2 is already 3, it's not possible. So meaning that is the maximum number compound that you want. Okay, so since there are 3 groups, meaning that 3 is equal M is equal to 3, you want acyclic, right? Okay, so if acyclic, okay, we have to choose Q equal to 1. Okay, and max is equal to 3 because maximum of 3 groups in the molecules. Okay, so you want to generate only until 3 groups, okay, in the molecules. Okay, so we can simplify here later. By next week I will explain again. Okay, what's the definition? So this is molecule that you can generate it from the 3 building blocks and the previous one. Okay, so it's associated with the group vector. Okay, and is based on the Orgel Macchiato rules. Okay, the one that not satisfied with the Orgel and Macchiato rules are highlighted with this one, with the red color lah. Okay, and then this one I will explain later in the next class. Okay, since already 12 o'clock, 1 hour is not enough. Okay, I hope that you can read first, try to understand. For example, this one, right? Possible molecules 1, 2, 3, 4, 5, 6, 7. This is 7 molecules that can be generated. Group vector, if you look at here, that CH3, we have a 2 CH3, this one CH3 OH, 2 1 CH3, 1 OH, and so on. And number of molecules for acyclic, this one 2, right? This one is 2, this one is 3, this one 3, this one is 3. Okay, Q, because we want acyclic, right? So of course 1. Okay, and then rule number 1, rule number 2, 3, 4, 5. Okay, so if you follow this one is valence, number of valence. This one is UJ, what? The number of valence UJ, and J is this one CH3 lah, right? That for that groups. Okay, if you look at here, if you insert, right, 2 minus with the how many valence? 1, right? CH3 only have 1. Okay, only 1 valence, and times with, because we have 2 CH3, so times with 2 equal to 2. Okay, so equal to 2 lah. Okay, okay, and then this one, right? 2 minus 1, because the valence is 1 lah. This one valence also 1, only one molecule each, so 1 1 equal to 2 lah. Okay, and so on. However, for this one, CH2 CH2 CH3, 2 minus 2, because this one is 2 valence and two groups, one valence and one group is equal to 1, is below than 2 lah. Okay, so this is not feasible. Okay, and what else? This one, rule number 2. So if you look at here, if we define CH3 as a J, and this one if we want to calculate first lah by using this equation, right? So if you look at here, Ni is equal to 1. No, sorry, this one first. This is not, we cannot calculate because we have only one group, CH3, right? So not available lah. Similarly also for OH, is not available. Okay, so we cannot calculate actually. This one we have J and I. J and I meaning that J for CH3, I for OH, or J for OH, I for CH3. So let's see for J is equal to CH3 lah. If J equal to CH3, if J is equal to CH3, okay, and I is equal to 1 lah, because OH as a I equal to 1 lah, right? And then NJ is equal to 1 also, 1 molecule, okay, right, 1 1. And then 1 minus 2, because the valence for the CH3 is 1 plus 2, so equal to 1 is over than equal or more than 1. 1 minus 2 is equal to negative 1. Negative 1 times with 1, negative 1 plus 2 equal to 1 lah. So it's feasible. Similarly, also you can do for OH. Okay, how about this one? CH2, right? CH2, J as CH2, I is equal to CH3 lah. So meaning that 2 for CH3. Okay, 1 minus 2 minus 2. Valence for CH2. So 220 plus 2. So is 2 is more or equal to 2. So it's feasible. This one is not feasible. Why? 2 minus 2 is equal to 0 times with 2 is equal to 0 lah, times 2. So meaning that 1 not feasible. 1 more or equal to 2 is not feasible lah. That's why it's a red. Okay, so CH2 CH3 is not feasible. Okay, it's already red color, right? This one. How about this one? Almost 12 o'clock. Sorry, CH3 0 lower bound. They have 2, right? This one. Okay, and J is equal to lah. Okay. Similarly, also this one. Maximum is 2. Okay. Upper bound. We have 1 CH3 and O. This is upper bound is equal to 0, right? However, for this one, if you look at here, that our upper bound is only 1 for OH. If you remember, can appear only 1, the maximum. Okay, but this one is appear as a 2. That's why it's red color. Okay, and this one NJ equal to N max. N max, this one we can represent as a 3. This one is a 2 and 2 lah. Okay, 2 2. This one is 2, right? And we can check also N equal to NJ. This one 2. This one is 2, 1 2. This one is 3. 2 plus 1 equal to 3, and so on. So if look at here, if we summarize, only the molecules that blue color is feasible. Okay, this one. This is only the molecules that are feasible. This one is not feasible. This one is because I'm not obey the rules. Okay, this one also not obey the rules. This one is not stable because there is another balancing. Okay. So I would like to summarize that generation of molecule structure actually we can generate a larger set of the functional groups, right? Okay, even a millions of chemical feasible molecule structure, for example, this one, okay, with the number of valence, okay. So, but we can reduce actually, we can screen based on all the rules, what you want to generate, okay. And since you will learn the ICAS software also, so we can screening actually. So we have no problem. Okay. So that's all for the molecule structure. For the next slide, class, I will explain this a little bit more. Okay, if too fast today. And also we will move to the generation of the mixture blend structure based on the equation of the Gibbs energy. Okay, I hope that you still remember this equation since you learned in the chemical engineering thermodynamics. Okay, that's all for today. Thank you very much. Sorry, it's already 12 o'clock. That's all. Okay, thank you.